In this lesson, we're going to examine the idea of rate of change. Rate of change is a really important idea in math. It's actually the whole idea of the study of calculus is how things are changing. So how fast something is growing, how fast it's moving, how much it's costing, how things are changing, usually over time. That's kind of a constant idea. Okay. When you have a graph, that's the easiest way of examining how something is changing. Is the graph going up? Is it going down? How fast is it going up? How fast is it going down? Is that rate changing over time or is it constant? So look at the first little example here. We have the distance from a wall versus time. At the beginning of time, we were right against the wall, but over time it's going down and down and down, which means it's getting further and further and further away. But the rate is constant. That line is straight. We can actually calculate the rate of what it's changing by figuring out the distance over time, or in other words, speed. And we can do that just using the idea of slope. Slope, or rate, is how that line is changing over time. And that's pretty straightforward to do with this nice straight line. But what if our line is changing? What if our line is curving? Well, since the line curves, the rate of change is going to be constantly changing itself. Okay, so just to draw a little picture here, if I had a curve that went up and then down and then up again, well, it was increasing, then decreasing, and increasing, but not necessarily at the same rates. At this point right here, it's going up pretty steeply, but here, not so much. Here, it got no change. It went flat, and then it was going down. Right? So our challenge is we have to talk in lots of cases about how our rates are changing at changing rates. So these nonlinear functions, what are we going to do with these? Well, from higher functions last year, we learned there's two different types of rates. There's an average rate. So the average rate, or as you probably heard it, AROC, is the slope of the line between two distinct points. So on this graph down here, we've got point B, we've got point C. Over time, the graph went up from B to C, but things happened in between there. And it had this huge drop before it went back up. But if we smooth things out by taking an average, we kind of ignore that drop. The other type of rate of change you can look at is an instantaneous rate of change, IROC. It's the slope of a line that just touches the function. We call that a tangent. That's a really important word for us in calculus, okay? Here in the diagram, we have a tangent at A. We just touched that graph. We can figure out the instantaneous rate at that specific point by figuring out the steepness of this line. The trick is that line only touches that graph in one spot. So we'd actually have to know something else about where this line starts or where it ends to figure out that instantaneous rate of change. That's kind of our big idea for today. We'll look at some AROCs and some IROCs to get ourselves an understanding about how this is going to help us in calculus. So our first example, the graph below shows how a cyclist accelerates away from an intersection. So at the beginning of time, they're at the intersection, they start pedaling, it gets faster and faster and faster until they start getting further and further from the intersection. I want to find some things out about that. Part A, what is the average speed over the first 5 seconds? So using the word average, I know it's an AROC. So I can figure out the average rate of time if I figure out what's happened between 0 and 5. And I can do that, and I can even put a line on here and say, here's my average rate of change. Sorry, I missed just a little bit there. Nice straight line. What's the steepness of that? Well, my slope equation, which is y2 minus y1 over x2 minus x1, tells me 25 minus 0 over 5 minus 0, that on average, that cyclist was moving at 5 meters per second. Well, we know by looking at the graph, it wasn't a constant 5 meters a second. At the beginning, it was way below that. It was slower. At the end, he was going way faster than that. It was over the line. But in general, that was his average speed. Okay, if we do part B, part 1, okay, what is the average speed between 2 and 5 seconds? And again, I know it's average because I got two distinct points. We're still doing AROC, but now I got to figure out what's happening at 2. So I'm going to have to estimate. Now, you're going to have to take your best guess and say what you think that is. I'm going to call that 2 and 5. Okay, that's 2 seconds. He's gone 5 meters. So for my AROC here, 25 minus 5 5 minus 2 will give me 20 over 3, which is 6.666 or 6.67 meters per second. So in that first little bit, he was actually going faster than average. Average was 5. From 2 to 5, he went faster than that, which, well, my line's curving up. It's getting steeper. That makes kind of sense. If we do part 2, from 4 to 5. So again, it's A rocks. There's 2 distinct points. I can tell them apart. We're going to have to estimate what's happening at 4. I'm going to call that 4 and let's call it 16, okay? So my slope equation still 25 minus 16 over 5 minus 4 tells me, and now he's going 9 or 9 meters per second. He's going even faster from 4 to 5. Okay, if I were to draw that line there, that secant would look like that. And it's almost the same steepness of the curve. It's definitely way steeper than the red line we started at. And then we do part 3. I want to do A rock again, because I have 2 distinct points from 4.5 to 5. So we have to estimate again. I think 4.5 is right here on the line, which is kind of nice for estimation. So 4.5 and 20. So our A rock will be 25 minus 20 over 5 minus 4.5, which is 5 over 0.5. In other words, 10 meters a second. It's even a better estimate of what's happening as we get closer and closer to 5. So based on the numbers we have so far, we can kind of get an idea what's happening the closer and closer we get to 5. In other words, we can kind of figure out, for part C, what is the I rock? What's happening at 5? The closer and closer our secants get to that point, the better and better our estimates. But the best estimate would be to draw a tangent. The tangent just hits that line right there. But in order to do that, to figure out the rate of that I rock, we need to have points that are on our graph. So we need to kind of estimate what is that number. And, well, we know 5 and 25, so I can use that. The further away your points are from the tangent, from the instantaneous value you want, the better the estimate's going to be. Like the best numbers you could probably use would probably be this one. That's as far to the left as the graph goes. And this one as far to the right as the graph goes. So I'm going to estimate using 8, and that looks about 70 to me. And this one right here is 3.5 and 0. So if I want to figure out what's happening at 5, the I rock, I know it's going to be slightly more than 10, as I'm getting bigger and bigger and bigger as I get there. But how much more than 10, I can't really tell until I figure out the I rock. So let's give it a try. So we said 70 minus 0. We're still using our slope equation. Nothing different there. And 8 minus 3.5. That would give me 70 over 4.5, which comes out to 15.555555 meters per second. As I said, the further your points are away, the better the estimates are. But again, they're still just estimates. Maybe I said 70 and it should have been 68. That could have a big difference. Maybe I said 3.5 and it should have been 3.7. That could make a big difference. I rock is pretty hard to figure out from a graph because it's all done by eye, the steepness of your line. And so I'm hoping as you're already doing this, and you're going to try the next one yourself, right here, that you're kind of thinking this method is, I don't really like this method. How do I know if I drew my line straight enough or I put in the best spot? And down the road, we're actually going to develop an algebraic model. I'll get rid of this by eye thing because it works, but it's not great. Okay, last example for today. Just a warm-up lesson here. Try this. I would pause this one, see if you can try it yourself, so you got this thing figured out. If not, come back and check, and we can go from there. So an experimental breeding colony of gorillas set up, and the size of the colony at time t is given by the graph below. So t is years, n is gorillas. What was the initial population? Well, the graph started at 60, so there were 60 of them. How fast did the population change over the first 5 years? That's an A-rock question. There's distinct points in time. So I need to figure out what's happening at 0, which I know is 0 and 60. And what's happening at 5 years? 5 years, right here in the middle, looks like 5 and 100. Okay, so AROC, 100 minus 60 over 5 minus 0 gives us 40 over 5. Or in other words, 8 gorillas per year. So our population is going up by 8 gorillas every year. How fast does the population change in the 5th year? Okay, keywords, in the 5th. That's an IROC question. So we're going to put a line on our graph at 5 that just touches a tangent. And we're going to have to do some estimation. That's kind of crooked there. I have to fix that. I don't see that. That's a little bit better. I'm hoping you guys will use your rulers. Okay, so I can say this one right here. That's like, oh, what's that? That's less than 1. I don't know. Is that 0.8? 0.8 and 0? Because 1 would be right in the middle, right? 0.5. Again, I'm estimating here. And what do we got over here? This is 10 years. 10 and what's that? 160, 70, 80, 90 maybe? That looks pretty close to that. But again, I'm estimating this is okay, but it's not great. So IROC, 190 minus 0 over 10 minus 0.8 gives you 190 over 9.2. So if we type that into our calculator, we end up with 20.65. So what happened in the 5th year? The population increased by 20.65. That was the rate of our increase. Again, every time you draw that line, you might get a slightly different answer. It depends on your estimation, depends on the straightness of your line. You and the person beside you might draw it slightly differently. So it works, but it's not the greatest method. Okay, how would you describe the rate of change over the population over time? Well, it's going up. Our graph is going up to the right. But it's not going up at a constant. It seems to be getting steeper and steeper. So if we're describing that, we'd say that the rate of population is increasing, is going up, but it's increasing at an increasing rate. Okay, so going up. It's going up at a faster and faster rate. It's getting steeper and steeper and steeper. That's how we can describe that population. Okay, so that's our first lesson in this unit, this introductory idea of calculus, that we can want to talk about rates. And we can do it by looking at graphs. We can figure out AROCs and IROCs, secants and tangents. And they're okay. Graphical methods are okay. You can get an idea of what's going on, but they're not great because everybody's going to have slightly different answers. That's kind of our key here. We need to start with this. We want to move to something a little bit more better, if you will. So I've got 2 little questions for you to try. Try them, see them. If you can't figure them out, come see me. And then we'll move into a more algebraic method in tomorrow's lesson.